Technion in Haifa, Israel, and I'm about to talk about my paper, verification of neural networks, local differential classification privacy. As I said before, if you understand each word separately, this is enough for the start. The words are only connected in this paper. So let's get it. So first of all, neural networks. So we know neural networks, they're very strong, but they're also vulnerable to privacy attacks because we use training set to train them. The training set contains sensitive information. And the privacy attacks can use this sensitive information that exists in the training network to extract or infer the sensitive information. Even in black box settings, and for example, the membership inference attack can infer whether a sample is a member of the training set or not a member of the training set. And it can be very problematic in many settings, privacy problematic. So when we talk about privacy, the most popular and common is called a way to quantify and inject privacy is called differential privacy. And what does differential privacy mean? It means an algorithm is differentially private. In our case, a network training algorithm would say it's differentially private if the result of the algorithm, aka the trained network, is or has a similar probability distribution, whether it was trained on the full training set or whether it was trained on a training set that is different in one sample, a differential training set, if you will. So the full training set or training sets that miss one sample should look roughly the same. Make sense, right? One sample shouldn't really matter. So if it really doesn't matter, we say it's private or differentially private. And any algorithm can turn into a differentially private if we simply add noise after we did the private, use the private information. For example, in network training, we usually add noise after every gradient step. And this is all really great, but when we add noise, we decrease the performance of the network, which is undesirable. And also, we have to initially train the network to be differentially private for it to be differentially private. A network that was trained normally will never be differentially private because only randomized algorithm can be differentially private. So we would like, given a network that was already trained by a general training algorithm, we would like to quantify the privacy or give privacy guarantees on this network that was already trained without changing the training process. So since we cannot use differential privacy, we have to invent a new privacy criterion, which we call local differential classification privacy. And the idea is that to use the idea of differential privacy by looking at a training set that are differential in one sample, however, in a deterministic setting. And we basically extend a local robustness property in this differential setting, and this is how it looks. So local, we look at a specific neighborhood, and differential, we look at the training set compared to the training set that is missing one sample. Classification, we only look at the classification of the part, and this is the privacy. So we look at the network that was trained on the full training set and that was trained on a on differential training set for any sample that can miss. And then, if all of them are locally robust, we say that it is private, or LDCP in our case. right? And if it's not very clear, then basically this, by this definition, there is a very naive algorithm in which we can make sure whether a network is LDCP or not, and just by following the various steps. So for every entry in the dataset, we remove it and train the network without this sample. And then we check local robustness on our neighborhood. And if it's local, and if everyone, all dataset size plus 1 networks are locally robust, then we say, oh, LDCP. And else, no. And this is really great. It gives us the optimal result. If only not, we needed to train D plus 1 networks and verify D plus 1 times local robustness. So this naive algorithm, while it gets us the results we want, is not practical. So we would like to do it without training that many networks. So our idea is called Sphynx, Safety Privacy Analyzer via Hyper Networks. And it works in 2 steps. And the step and connecting them is a new object we call a hyper network, which is basically an abstraction of all the possible D plus 1 networks. And instead of training the D plus 1 networks, we predict a hyper network. And then, instead of verifying local robustness D plus 1 times, we verify LDCP once on the hyper network. And I will talk about each part. But before that, we'll talk about the hyper network itself. So, in order for our idea to work, we need to define what is a hyper network. What is this middle object? So, the hyper network is an abstraction of the networks. So, the way it works is that it looks like a regular network, but each network parameter or a weight, instead of a number, is an abstract element. And we chose the intervals because intervals are very simple, which helps us, but they're also not very super simple. Like we can tell some things about them. And if we have all the networks, then getting the hypernetwork is very easy. We take the minimum and maximum number for each weight. But we cannot do this because we don't want to train all D plus 1 networks. So we have to predict the hypernetwork from a small number of networks and cannot use everyone. So how do we do it? So we train a small number of networks, each one without a single unique sample. We predict a hypernetwork by predicting an interval for each parameter independently, which we can do because intervals are non-relational abstractions. And then we check whether our hypernetwork is good enough by comparing it to the hypernetwork from the previous iteration. And if they're similar, then we say the algorithm converged and we're okay, and else we go and train more networks. So we'll be also adaptive about the number of networks we use depending on the difficulty of the problem. So now we'll talk about how we predict an interval. So when predicting an interval, we reduced our problem from predicting a hypernetwork to basically having a few samples from an IID distribution. And we don't know what the distribution is, but we know we have samples from IID distribution, and we want an interval that covers all the samples from the same distribution that we don't see. If we knew what the distribution was, it will be very easy. But we don't know. And we cannot assume we know. We cannot assume, for example, we cannot assume it's Gaussian, because to just be a lie, right? It's real data we train. So the idea is that we'll transform the values into a distribution we know, and the distribution we know will be using a kernel density estimation, which is good for estimating, but we not just use kernel density estimation to estimate the distribution, we'll also transform the data into something it will be easier to estimate. And it works like this. So first we normalize the data, which is very important because it centers it around 0 and make everyone the same scale. And then we transform the data into the distribution. And then we compute a confidence interval. And eventually we undo the transformation normalization on the interval to get an interval for the original scale. And this is won't go into the specifics of this, so we'll just have the one. All right, so this was the prediction part, and now the verification part. So the verification of hypernetwork is very similar to the verification of local robustness of a normal network. We exchange a normal local robustness verifier, specifically the mixed integer linear programming verifier, which we use because it is a complete verifier, and it doesn't induce any over-approximation, which is very important because the existence of the hypernetwork already induces over-approximation to our problem. So we don't want to induce more over-approximation, make it unsolvable. So we have to use the strong verifier. However, using a naive extension, we lead to quadratic constraint because the linear layers, we have a weight times neuron. And this time, both the weights and the neurons are parameters. So we cannot do a naive extension. However, if the layers input are non-negative, then we can bound it using the upper bounds of the weights and biases and the lower bound of the weights and biases, because the input is non-negative. And now, instead of each linear layer, instead of having one equality constraint, we replace it with two inequality constraints, which is the same complexity. And the activation layers don't have any parameters, so their encoding remain unchanged. So this is the only difference. One equality constraints turned into two inequality constraints. All right, now about to evaluate. So we implemented the code online, and we use a 3 data-sensitive dataset, adult census, bank marketing, and default of credit card clients, nicknamed adult, bank, and credit. Here you can see the D+1 of each one. Big numbers. And each of them was trained on, they're all binary data sets. They have binary output. And we use, each of them was trained on 3 types of binary networks, of fully connected binary networks, 2 hidden layers of 50 neurons, 2 hidden layers of 100 neurons, and 4 hidden layers of 50 neurons. Right? And so how effective it is? So in order to talk about LDCP, we need to talk about the local part. We need a neighborhood. Without a neighborhood, we cannot talk about LDCP. So we use 3 types of neighborhoods. The membership neighborhood, which is just the sample itself. DP robustness, which is the standard local robustness neighborhood, infinity norm of size epsilon. And the sensitivity or individual fairness neighborhood, which is all samples that are exactly like our sample, except for one sensitive attribute, such as gender or age. So these are the neighborhoods we worked with, and we had 100 neighborhoods of each type for each data set. And we compared it to the naive algorithm to get true positive, true negative, false positive, and false negative. These are our results. So we can see membership is the easiest neighborhood, so a lot of true positive, not really much getting true negative and false positive, and few false negatives, very, very easy. We do have over-approximation, so we do get few false negative. DP robustness, a bit harder, so we have a few more true negatives. And also in sensitivity, we can see that the false positives that exist because the hypernetwork might have under-approximation are very rare. So it's a good thing. Right, and this is the running time. So you can see the number of trained network that the naive algorithm use, which is D+1, and our algorithm use, we see great improvement. The training time is proportional to the number of networks we trained, so you see the same improvement. However, the best improvement is actually in the verification, because instead of verifying D+1 times local robustness, we verify LDCP only once. And we do it once per neighborhood, so if we have a lot of neighborhoods, this is the bottleneck. So this super great improvement is very important. So now, how good we predict an interval? So we look only on the thing we call the weight abstraction rate, which is the percentage of the weights that are fully abstracted by the hypernetwork. That all of them are fully abstracted. So, and we compare a few variations of our algorithm. So we have the interval abstraction, in which we get a few networks and we get the minimum interval that include all of them. Get bad results. Minus transform, we do not transform the data before we assume we know what the distribution is and estimate it, and it gets moderate result. Minus normalize, we transform the data but without normalizing it first. Horrible results. Normalizing the data before transforming is important. Minus KDE, we do not use kernel density estimation and instead transform the data into a Gaussian distribution as normal, and also get a moderate result since we do use transformation. And predint, our algorithm for predicting an interval, it gets the best result because it uses all of the things together. By predicting a hypernetwork, we compare the interval abstraction to Sphynx, and the network abstraction rate is the percentage of networks that are fully abstracted by the hypernetwork and are fully included in the hypernetwork. And the interval abstraction, it really depends. It really depends on luck, but on our algorithm, we always get more than 90% of the networks that are included. All right, so in conclusion, we have a new privacy property, local differential classification privacy. We have a verifier that verify LDCP by training small number of networks, creating a hypernetwork, and verifying LDCP directly on the hypernetwork using normal local robustness verifier, a bit modified. And this is our results. We trained only 7% of the networks, and our hypernetwork contains more than 90% of the networks. Our verification accuracy is 93%. And the verification times is 17,000 times faster. So, any questions?
Hi, I have two questions. The first is, how is hyper neural networks different from abstract neural networks?
When I saw the abstract neural networks, the abstraction was completely different and for different purpose. When I saw when I search for what is an abstract neural network, usually they combine neurons together. Like you had one network, and you combine the neurons together to get an abstraction of the single network, so that the verification process will be faster. But here, we have multiple networks, and we use one network to abstract all of them. So it's a different thing.
So you're joining networks instead of joining neurons.
Yeah, but it's a different thing because it has a different purpose, and like we don't do it to make verification of a single network faster. Like instead of making a single network smaller, we join many networks that we all care about all of them together.
Okay.
So it's different. They're not related to each other.
So the second question was like, given the threat is the loss of privacy, like have you considered the work in the context of federated learning?
What do you mean about
federated learning, as in like the Google translator app, the Google keyboard learns how to predict the next word by.
Yeah, I know. Federated learning is when multiple agents work together for the same task.
There is a lot of work for privacy in that case, so could that be more integrated with your condition?
So the thing is, our algorithm need to train the full network from scratch. So for our algorithm, so the one who runs our algorithm need to have access to the private information. And in federated learning, nobody have access to the full private information. And that means that probably either we need to change it or it won't work, because you need some sort of a local agent that has all the private information and runs our algorithm. So it works more in the case of a single silo, that you just get it all, you have all the data and you take our algorithm and run it on your own computer, that the private data will not leak. So I'm not really sure how it will work with federated learning.
Thank you.
A quick question. Yeah, so is it possible to train a hyper network directly?
To what?
To train directly.
Yeah, so I thought about it, but the problem is every epoch, the intervals will increase and increase and increase and increase until they're not relevant, unless you have a really smart idea to use the old connections. Then you can use like something much smarter than the intervals. But the thing is, I still like the intervals, because the intervals make it both the prediction and the verification easier. Because even the verification, we swapped one equation with two inequalities because we had intervals, and not because of all other things. And also, it's really hard to track all the changes correctly. So yeah, it will be ideal if we could train it directly, but it's really hard because network training is not a simpler algorithm. So we'd rather just look at the results and compare them to each other.
Okay, so let's thank the speaker once more.